Hello, the next thing we're going to talk about is limits at infinity and horizontal asymptotes. And just as a quick recap, recall before we move on to horizontal asymptotes, if A is less than B, then this interval is called a closed interval. We include the endpoints, whereas this interval is an open interval. We don't include the endpoints. We want everybody in between, but we don't include the endpoints. Like if A was 0 and B was 1, we would include everybody in between 0 and 1, but not 0 and 1 themselves. Whereas in this interval, we not only include everybody in between, we include 0 and 1 themselves. And that's just the example when A is 0 and B is 1. A and B could actually be a whole bunch of things. But anyway, in general, they could be anything. They're arbitrary. I shouldn't say a whole bunch of things. I should just say that they're arbitrary. That would be a better way to put it. Arbitrary. Okay, let's move on. Limits at infinity or horizontal asymptotes. Let A be a real number and L be a real number. Let the reals be a superset of D, which is a superset of this closed interval A to infinity, and you can never put a bracket on infinity. Let F be a function from D to R. We say that the limit as x goes to positive infinity of f of x equals L if f of x gets arbitrarily close to L as x gets as x goes off forever to the right, and hence gets arbitrarily large in the positive sense. The horizontal line y equals L is said to be a horizontal asymptote of f, or of the function f of x. Let B be a real number and L be an element of R. Again, let R be a superset of D, which is a superset of negative infinity to B. Let F be a function from D to R. We say that the limit as x goes to neg infinity of f of x equals L if f of x gets arbitrarily close to L as x goes off forever to the left and hence gets arbitrarily large in the negative sense. The horizontal line y equals L is again, just like up here, said to be a horizontal asymptote of f. These are the... So either way, you don't have to satisfy both necessarily. You just need to satisfy one to be a horizontal asymptote. So I gave a few examples. These are kind of pedestrian, but they get the job done. Like, consider the function f of x equals 5 over x. The limit as x goes to positive infinity, and quite frankly, I could have went to negative infinity and I'd have got the same result. So the limit as x goes to positive infinity of 5 over x equals 0. And likewise, I already took care of that, didn't I? It's right here. Since 5 over x since f of x equals 5 over x goes to 0 as x goes to either infinity. So y equals 0 is a horizontal asymptote of f, and I got a typo there, when f of x equals 5 over x for all non-zero real numbers. So let me get rid of that of. Too many ofs. So now, to be honest with you, I just needed to show one of these to demonstrate that it was a horizontal asymptote. You know, the fact that both are here is always nice, but I just need one of them, to be honest. Either one of them to work. Let f be a function from the non-zero reals to the reals such that f of x equals 1 over x if x is negative, while f of x equals this, 2 minus 3, quantity 3 over x, if x is positive. And we'll just leave f of 0 undefined. It doesn't really matter here. Recalling algebra, we get that the limit as x goes to negative infinity, which is, remember, since on the negative side we're 1 over x, it's the limit x goes to neg infinity of 1 over x. That's 0. Whereas the limit as x goes to positive infinity, and again, remember, I'm using plus infinity and ordinary infinity interchangeably. Limit as x goes to positive infinity of f of x. That equals the limit as x goes to positive infinity of 2 minus 3 over x, but that's equal to 2. Okay, that's fine. That's fine. There's two different limits, but we're going to two different infinities anyway. So we have two different horizontal asymptotes. Each one is as good as the other. They're both, and when I say horizontal asymptotes, I should say horizontal asymptotes of f, just to not be hollow. And those two horizontal asymptotes are y equals 0 and y equals 2. So what's going to happen is, as the graph goes off a long, long way to the right, as f of x, as the graph of y equals f of x goes way, far, far to the right, y equals f of x is going to get arbitrarily close to 2, but it's never going to quite touch 2. It will get closer and closer indefinitely without ever touching 2. That's kind of a strange thing to think about. And in a similar fashion, as y goes off forever to the left, on the other hand, as it goes off to a negative trillion, 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 and beyond, and as it keeps on going to the left, y will zone in on 0, which is the x-axis forevermore, but it will never quite touch it. It will get indefinitely closer and closer through all eternity as you go to the left in the Cartesian plane, but it will never touch y equals 0. That's kind of a strange thing to wrap your mind around if you think about it, but it's true. I know a picture would be warranted, but to draw graphs is a little bit awkward. But I may graph this later. I'm not going to swear by it, but I might graph this later. But following my cursor, like as f of x gets close to 2, then you're going to forevermore zone in on 2, but you're never going to quite touch it. You're going to flatten off. You're going to get pretty much flat as you go a long way to the right, but you'll never completely get flat. You'll never touch y equals 2. You would have to go infinitely far to get to actually touch y equals 2, but you can't go infinitely far. You just can't do it. And infinitely far to the right, I should say. You'd have to go infinitely far to the right. And whereas for y equals 0, you get close to it. As the graph of f goes way far to the left, you zone in on y equals 0 on the other hand. But anyway, that's that for horizontal asymptotes.